All right, so I'm going to talk about my lab, which we call Modlab. Essentially, it's going to be a bunch of different projects that people are talking about. The project lead in this particular case is Andrew Spechen. So one of the things we've been working on is what we call edge rolling. If you have a large object that's too heavy to lift, one way to manipulate it may be to roll it. So we come up with doing a dynamic analysis for how it rolls is actually not that easy, but we have been able to get things to roll. He also has a project that we call Corey, which is a humanoid robot. And in this case, this is a video of the robot in the Philadelphia Museum of Art. We are currently looking at having that robot interact with elders and for elder care to see if we can help them do things with like exercise. This is another project James Picoul will also be talking actually next week. We have another set of 9 professors talking next week. So we are doing some soft robotics. Jessica Yin is looking at sensors that can both do proximity detection as well as contact analysis. Greg Campbell is working on clutches that can change the shape of a soft robot as it has under pressure. Again, James Picoul will likely talk a little bit more about that next week. Another project is what we call the variable topology truss. In this case, we have a robot that's made up of prismatic joints, so it can change its shape, can also rearrange the topology of the arrangement of joints. This is the physical system in perch, the video sped up. So we can have it kind of walk around as well as change its gross shape. One of the nice things about having a robot that has lots of prismatic joints that can change the size is that the robot could theoretically shrink to a small size to get through small gaps and then expand again to move faster. Jean Cobet is the contact point for that. It's actually a relatively large project. Another thing that that's kind of interesting is if you want to change shapes, how do you change shapes is not that clear. And one of the things especially if you need to change the topology, Alexander has realized that you can using knot theory, we can come up with invariants to determine whether you actually need to reconfigure. So in this case, the picture on the left is like a starting position. The next picture is the goal. So here's another one that's initial position, and this is the goal. Turns out that by using this invariant analysis, you can quickly realize that you don't actually need to reconfigure. There's a rotation and a relabeling of the nodes will actually get you to where you want to go. This is a swimming robot. It has one motor. And if you look carefully, you can see these little flappers that come out with each stroke. So with one motor, you can actually get this robot to swim around different places. One of the things that we like to do is have these robots dock together to form larger systems. So anyway, the robots can be precisely controlled to dock, and then we can have group formations. How do you control the different robots when they're docked together to form, to go to different places without accidentally undocking? We have another project. Again, it's a one motor system, except this time it's flying. So we have the world's record for the smallest flying robot using one motor. This is a work that's joint with Northwestern. The idea is we're going to build 200 of these and have, because they're small, they're safe. If they bump into you, they're not going to hurt you. Can we form different shapes with them? A couple of things about that is how do you deal with the problem of battery life? These things only go for like a minute. So the idea is we rethought, instead of having robots that hover, we have them following a path and then landing and recharging constantly. By using something like supercaps or ultracaps, we can quickly recharge them and essentially you form the shape by having robots go through that path. The other problem that we have is that if you've got this big swarm, the downwash will usually cause problems. Causes the other robots flying underneath them to crash or other things. So we're trying to see if we can curate a system in which we shape that downwash to be a little bit smaller or more easy to work with. Another project is we're in the Guinness Book of World Records for the first ice robot made of ice. The idea here is that you could send parts up to like Antarctica or the moon or someplace where you have ice, and the robot can build its structure from that ice. Whether you want a robot arm or build wheels, or if they break, you can get ice all over the place, so you can just make new parts. I think this is the last slide. We have a project where we're trying to look at swarms of microrobots. So Marc Miskin will talk later today about his robots, and we're thinking about if we have thousands of them, can we actually use them to build things? And especially if they have local rules to do things like this box in the middle is kind of like a shape of like bamboo. I don't know if the timer didn't go off. Anyway, so we're also trying to understand how do robots, how do they actually maneuver? How do they do? Can we get them to turn and go backwards and forwards and all that kind of stuff at the micro scale? CJ Taylor is next. So also between each speaker, I think we've got 1 minute. So if there are any questions while we're swapping over, we might have to be able to do that real quick. Any quick questions? So there should be a call.
Okay, I guess that's me. So I'm going to try to go through way too many slides in way too little time. So yeah, please feel free to come find me if there's things about this that interest you. So there are a couple of things that I'm interested in. I guess the general theme I like to point out is this idea of sort of spatial intelligence for intelligent systems. I'm really interested in systems that can actually perceive the world and then act accordingly. So there are a number of contexts in which we do this. So this is one project that we did, which focused on flying robots. So building systems that could actually autonomously approach buildings, enter them, explore the terrain, and so on. So the aspect, this is absolutely joint work with a number of people, including Vijay's group. And so we did everything for the system, from the construction of the computing system, from design of the perception system, control, the whole 9 yards. So a lot of interesting and fun aspects that come out of this. There's sort of room for a lot of different interests and capabilities and skills. This is one of the systems that we're working with currently. This is our new Falcon system. It has a number of features that we like, including really, really long battery life. It has a built-in 3D LiDAR system, in addition to a home-built computer vision system. So this is an idea of sort of some of the stuff that we do with this system playing. So you just have to imagine that this thing is in fact flying and doing what it should. We're using this for, again, a variety of different purposes, from agriculture to life. Another kind of platform that I've actually been very interested in recently is legged platforms. So this is actually one system built by Ghost Robotics, spin-off from Chen. And I'll show you a little bit later some of the work that we're doing that focuses on trying to link perception to action for these kinds of systems. Okay, a bit of a different spin on looking at perception for action is trying to build sort of higher level understandings of environments. So this is a work of a former student, Arman Shariati, and his work dealt with the problem of building floor plan representations from sensor data. So given the kind of data that a robot might acquire as it moves around in an environment, how can we actually parse that data and build a parsimonious representation of the scene? So in this case, the system walks through and it actually automatically decides that this looks like a hallway, this looks like a room, this looks like a doorway, and it actually sort of does that through what we think is a pretty interesting convex optimization framework that allows us to sort of automatically extract these features and propose this as a reconstruction, which allows us to do much better job of SLAM than we could from the raw sensor data that we were using in this kind of for this kind of system. Okay, this also works in 3D. I guess I'll show enough of this to hopefully convince you. This is actually data collected from a row house in Philadelphia. So it's a 3-floor system. We are mapping this with a LiDAR sensor. We're going upstairs, downstairs, and the system is automatically deciding where the floors are, where the walls are, figuring out what's going on, and building a reconstruction accordingly. Yeah, we're able to do this in real time, given the scheme that we're doing. Okay, here's some other work that's actually from my student Chad, who is actually going to be presenting his thesis proposal today later today. His work is dealing with how do we actually fuse information from a LiDAR sensor with vision sensors. So in this case, let's say you have sparse information from a LiDAR sensor, but you have a 2 megapixel or 3 megapixel image. How do you actually go from the sparse story on the top to a dense story on the bottom? So this is something that we've actually gotten pretty good at. We've also been able to extend this work where we, by adopting a Bayesian framework, we're actually able to also tell you about the uncertainty in our estimates and actually do that in a very, very controlled way that improves upon a lot of other schemes that have been proposed previously. Another piece of work that was done relatively recently was by my student Anthony Cowley, who is working on, explored this idea of representing the world using these local panoramic representations. So think of the world as being divided into places, and in every place you kind of have an image for what the world looks like that encodes sort of the 3D structure. The advantage of this is twofold. One, it leads to extremely efficient algorithms. We're actually able to build systems that can do real-time modeling of these kinds of systems as the systems move around. We've tried it on a number of different platforms, so wheeled, legged, flying, and the like. The other thing we were able to do is build very, very parsimonious representations of space. Turns out that these are actually don't use a whole lot of storage. And we can use the resulting panoramic images for a number of other things. I'll show you one of those going forward. Okay, so for instance, we've applied this to model entire cities in Western Pennsylvania. So we're able to capture a scene like this, 4.4 kilometers worth of driving, just a little over 1 gigabyte of space. Some more recent results we actually have in this area is that my student Chow has been working on improvements to this. So we now have real-time LiDAR-based odometry systems that work in single-digit milliseconds on CPUs without GPU acceleration. That's really fun because it now means that we can apply this in control loops. We can use this to do real-time analysis of indoor and outdoor scenes, and we can provide these systems as input to other systems like this one. So here's another way of looking at spatial intelligence where we were actually looking at the problem of localizing ground-based robots based on information from aerial robots. So the way I like to think about this is that this is the kind of problem that you face if you're a tourist in Paris, where you've never been there before, you're looking around you and you're trying to figure out where you are in the scene. For some reason, this is not playing. What our system is able to do is it does a semantic analysis of the space around it and observes things like I'm next to a tree, next to a building, across from a river. And then based on that, it actually looks at the overhead image and finds if there are any locations that actually have that same semantic structure. And that semantic analysis is very important because the world looks very different when you're up high and when you're looking at it at the ground. But the semantic context is the same. So a river is a river, a tree is a tree, a building is a building, even if they look completely different. So again, using the panoramic representation that we've been able to build in real time from data, we're able to fuse this and do a good job of localization. Two more things I'll just quickly go through because the video is actually played for this one. This is some work of my student Hirsch Sangvi, who's actually looking at this problem of planning footsteps for legged platforms. And the trick here is actually doing this fast enough that it's relevant. So legged platforms are great, but you need to be able, in order to get the everything out of them, they need to be able to link perception to action and decide where they're going to put their feet. And this is actually a very, very tricky planning problem. So we've been developing these neural network-based schemes that allow the system, us to plan for these highly dynamic systems in real time. Last thing I'll show, this is again joint work with some folks in Kostas' group and in Annie's group. This is some work on real-time catching. So in this case, we're using information from an event camera. We're actually firing ping pong balls at it at high speed and using the data from the camera to actually decide where the ball is going and actually move back and forth. We actually have other work in this area that's actually focused on allowing us to build other kinds of representations over the fact. So I'm going to stop there. All right, thanks, Vijay. Any other questions for Vijay while we're starting over? I think you're running.
Okay, so I'm Pratik Chaudhari. I work on robotics and machine learning. If you have any questions, you're interested in these projects, please feel free to email me. I will talk about 3 different things today that we are doing in our group. The first one is about understanding deep neural networks using tools in statistical physics and information theory. And since a lot of you are beginning your research, I will tell you what I did for my PhD. This is the kind of questions that I asked for in my PhD. We know neural networks work well. We know that simple algorithms like SGD work well for training them. Why is it that these simple algorithms work well? Once you kind of get an insight into some of the peculiarities of these algorithms, you can design better methods to train neural networks. So we have methods that are about 4 times faster than SGD, give or take. We understand a little bit more of how algorithms like SGD train neural networks. And these days, we are interested in exploring this direction using 2 perspectives. So just like if I were to ask you for the temperature of this room or the pressure of air inside this room, you don't really care about knowing the locations of all molecules. What you care about is this big ensemble quantities. Similarly, in order to understand a neural network, you may not be interested in, you don't have to understand every particular neuron. You can look at the neurons as an ensemble of neurons and use tools from thermodynamics and statistical physics to make predictions of how the network will behave, even if you don't know the little details here and there. So as like a big a picture story, we would like to build the first law of information or the second law of information. What is it that you cannot do if you don't have sufficiently rich data or you don't have sufficiently enough data? And these are the kind of things. There's a historical precedent for this, of course. Steam engine was built about 100 years before we understood thermodynamics, and we are kind of in the same spirit. There's a second way that we look at these things, which is to understand the space of functions that neural networks express. We believe, and I could be wrong, that different neural networks trained on the same data set are essentially the same. So if you draw like a big manifold of all the predictions that the neural network makes on n training samples, this manifold has certain special structure. It may be thin in certain places, it may be thick in certain places, and this lets us study the kind of representations that neural networks learn. This lets us study problems in multitask learning, in continual learning, etc., using these kinds of tools. Okay, so this is about learning neural networks. The second theme in our group is about how to learn with few labeled samples. So machine learning has always been about the limit as the number of data points goes to 0. Traditionally, we have kind of ignored this or forgotten about this, and we have always tried to think about the number of samples going to infinity. But really, like if you're a good machine learning algorithm, you have to work well with few samples. So we have some very powerful ideas, I should say, on few short learning style problems. We have explored these ideas for problems in meta learning. So think of a robot whose sensors may break down during the course of its operation, and it would like to adapt its policies or controllers to mitigate such failures. There's another direction that we're exploring using these tools, which is in the regime of medical imaging. So one very, very special and important property of medical data is that no 2 people are the same. So your brain, my brain looks totally different. We have different striations on the brain that are very important if you want to do anything, any diagnostics. And understanding such diversity in the data is critical if you want to do good machine learning with such data sets for these applications. So we have tools where we can study how to specialize deep learning models for small sample sizes, be they racial minorities in the population, or be they more so people of age groups larger than 75 years or so. So we can fine tune our models to give more accurate predictions for such groups. One work that I would like to highlight here is a recent work that we have on multitask learning and continual learning. And spiritually speaking, AdaBoost. AdaBoost is one of the most influential algorithms of the last 30 years or so. It takes your data set and then splits the data set into little pieces and then fits little models for each subset, right? We like to do the same thing for multiple tasks. So give me 100 tasks. I would like to sample a set of tasks, and I will sample a set of synergistic tasks, the ones that help each other's learning, and then build little models for each of them. And at the end, I combine these models together. So this is a very good algorithm as far as we have tested it. And it performs dramatically better than existing algorithms for these problems. Let me skip this slide. The third theme in our group is offshoot of some of my master's work that I did on autonomous driving. So it began a long time ago, at this point of time, 8 years ago, where we're building some of the first autonomous cars, little cute ones, this golf cart that could pick you up. Over the course of the next few years, it transitioned into this company called Autonomy, which operates in Boston and Singapore now. And by then we could do a bunch of non-trivial things, navigate closed spaces, drive around in the city, essentially without interaction by the driver for a long periods of time, etc. These days, we are particularly interested in unstructured environments. Cities are very structured, forests are very unstructured. This relates to something that CJ talked about. So we would like to use the Falcon platform, the drone, and we want to explore a forest. We want to map very large areas. So think of like 1,000 acre in a forest that you're mapping for little details, all the way from the volume of the timber in the trees to knowing the species of different trees, understanding how much carbon is captured in these trees, so on and so forth. So here you will see problems in like SLAM, object detection, semantic segmentation, etc. Okay. The next problem that I would like to showcase is very large multi-agent reinforcement learning problems. So think of a team of 1,000 agents that is trying to fight against another team of 1,000 agents. And we can do deep reinforcement learning for such very large problems. So this is, I don't want you to read the plot too carefully, but this is by our estimates, one of the largest examples that we've seen of training deep learning. To conclude, it's a big and diverse group. We had a bunch of very enthusiastic undergraduates over this summer. Join us if you are interested in this problem. Thank you.
Okay. Hi, I'm Ken Chaney. I work in Kostas Daniilidis' group. We're a group of about 17 PhD students. I actually think looking at the slide is the first time I realized it was that many. And 4 postdocs, as well as a large number of master's students and undergrad students. And we actually also have a large group of relatively active recent alumni. So the current 3 areas of interest are neuromorphic sensing, geometry, and curious robots. These 3 topics sort of encompass most of what Kostas Group is currently doing. So neuromorphic sensing is near and dear to me because that's my research area. So specifically, I do research with event-based cameras. Event-based cameras are novel asynchronous sensors that respond to changes in the scene instead of just sending frames back. So for a standard camera, let's say an iPhone, it shoots 240 frames a second, which means you're going to be getting entire image frames at that rate. Whereas with event-based cameras, if nothing changes in the environment, then you only get a little bit of noise events coming out of the sensor. Whereas with a standard video stream, you're left with a ton of data. These cameras have numerous benefits. So they also, do I get a laser? Yep, I get a laser pointer. So you can see that we continue getting events even when you don't have any actual grayscale information coming out. I mean, I could go on and on, but those are a couple of the primary benefits. Okay, sorry, the slides are being a little bit weird. So the next component for Kostas's work is geometry. So one of the big components is equivariant representations. This was work that has started back when CNNs really started to become popular. The question was asked, well, how do we work symmetries in the world that we know about explicitly into neural networks? And so you can see feature maps that are learned that rotate as the shape that's being analyzed rotates with it. And then the output feature vector after a max pooling layer is actually constant because you're analyzing the same object. So this is another work that's similar to that. Icosahedral group convolutions on the set of views. Essentially, this asks the question of how do you analyze multiple views of the same object in a coherent manner. Find out. Does anybody know what this Zoom thing's about? Sorry.
All right, well,
Okay, sorry about that. Oh, where was I? Okay, so essentially this work takes a different viewpoint on similar problems that people answer with just CNNs, but takes a more mathematically rigorous approach to it. Yeah, sorry. Why does this clicker? Okay, so work that we've been doing recently is in the reconstruction of 3D meshes for both humans and birds. They might seem like sort of very different concepts, but the fundamental techniques are very similar between the two. However, each do have their own unique set of challenges. Nikos Kolatoros is one of the PhD students in our group, and he's been doing most of the 3D human reconstruction work. And essentially what we try to do with this work is replace the need for a very expensive mocap system. So traditionally in the movie industry, how you get these 3D meshes and tracking of people is you set up 20, 30, 40 cameras and you put markers on the person, and then you track them as they move through that space. This is very limiting because you're limited to a particular volume, very expensive. This work leverages CNNs to produce a 3D mesh without the need for that very expensive equipment setup, just single camera actually. And birds are interesting for us because we've set up the PenSmart Aviary. This has about 12 cameras that record 8 hours a day for months on end. So we have this very large data set of birds. And while this might not sound interesting for people who don't really care about birds, this is very interesting because of the long period of time for this experiment, we're able to learn social behaviors and see how they interact over a very long period of time and see what sort of posturing birds do with either birds they're adversaries with or friendly towards. And this is in collaboration with the biology department. So another component for us is curious robotics. So learning to map and semantic navigation. Traditionally in robotics, how we've gone to a particular location is by telling it a 2D or a 3D coordinate to go to. But that's not how you tell another person to go find something. You tell a person, please go find a chair, or please go find a laptop. You don't say, go to 10 meters out by 5 meters over. So we're looking at how to explore an environment while building a semantic map to find objects of interest and alleviate the need to understand where things are before you know where they are. Do this real quick. So another component that we've been working on is how to learn in environments without rewards. I believe this is Oleg's work, where he takes a self-supervised exploration approach to help explore the world with an agent, and then based on that world model, he's able to train individual models to stand, walk, run, etc. All right, thanks, Ken. Sorry. Sorry about that. All right, Eric, up. Still working. Yeah.
All right, hello everyone. I'm Eric Eaton, and my group focuses on the problem of lifelong machine learning, and we're going to really broadly define this. So imagine we have a robot in an environment like a university, and in that case, it's learning the tasks that you might expect a robot in a university to do. It might learn to recognize that there's students sitting on the floor waiting for office hours, or recognizing tables and chairs in the bump space. But then we want to take a robot and have it learn new things over time. So maybe now a plant appears, or you want to task it to do something. You don't want the robot to just move around the space. You want it to, say, deliver a paper to a faculty member, or mail out packages out from a delivery room, or you want to find someone, or you want to have it take someone on a tour of the building, or bring someone to a particular location, greet students and bring them up to office hours, something like that. And then we take that same robot and we move it to a new setting it's never seen before, like a hospital, where now it encounters things like wheelchairs and walkers, and has new tasks like delivering medicine, or watching out for a patient falling out of a bed, for example, and patients incurring risks as they move around. And then we take it to yet another setting, and another and another. And the idea is we want to have the robot continually build upon its knowledge. So I'm interested in versatile AI systems. And what we want to do is we want to, first off, build intelligent systems that very quickly learn new things, just like you or I. We also want to enable robotics to continually improve with experience. And I'm not interested in systems that just learn one task. I want to do versatile learning, such that we can very quickly build on the skills or knowledge that we have over time through a combination of lifelong learning, interaction with the world, self-supervised learning, and the like. And lastly, I also contend that we don't do this in isolation. We watch other people, we interact with people in the world. And so how can we do this with interaction with humans and other agents? And so we're looking at this problem in lifelong learning very broadly defined. And there's many research topics that we work on. Here's kind of 3 highlights. The first is continual learning, or also called commonly lifelong learning in the machine learning literature. And in this case, what we're doing is we're building continual deep learning systems, both for classification as well as reinforcement learning. We've been looking at composable representations. These are kind of modular knowledge that you can combine together in a functional form, much like you would build up functions together in a programming language. So how can we build this knowledge together to solve a new task? And how can we do this in environments that change over time? The second big area of work that we work in is this idea of open world robotics. So instead of having a very narrow test bed that we have the robots running in, can we deploy robots that operate in the real world without the environment being structured for them? And so this involves detecting novelty and compensating for it, doing self-taught learning and exploration. And we apply these techniques to problems primarily in service robots and medicine. And so I'm going to talk of just the highlights of a few highlights from this work. The first is if we're doing deep lifelong learning. And what we're going to be doing in this case is watching a series of tasks. And these are classification tasks. And what do we see on the left-hand side here is a standard multitask CNN, if you do not have it enabled for lifelong or continual learning. And what you can see is that each new task, which is in a new color, the performance goes up, but then it drops very suddenly. And you can see the task that you've seen before continually being essentially driven down by interference within the network. On the right-hand side, you see our lifelong learning. And this is much more akin to how you or I learn, in that we build on our knowledge over time. We get better and better, and we don't have this kind of interference that's happening. And so you can see both performance being sustained over time, but you can also see that the transfer benefiting the learning and boosting the overall level of performance. We've applied this to reinforcement learning as well. So this is a approach based on lifelong policy gradient methods. And in this case, what we have is a simulated robot arm doing a variety of different tasks over time. Things like going to a particular location as the bare minimum easiest one, then using a hammer or operating a door lock or a basketball or a window or a coffee maker. And what you can see on one side is the left-hand side, in this case, the LPGFDW is our approach. And you can see, I'll pick one like the coffee maker, for example. You can see it slide the cup under while pressing the button with its kind of wrist, while as standard single task learning on the right-hand side knocks the cup over as it goes. So there's this benefit that is not happening if you learn tasks in isolation, that only comes from learning tasks and knowledge through transfer in a lifelong setting. We've been applying these to problems in autonomous service robots. And so we have a joint project with a large number of universities to take and do what we're calling a scavenger hunt. So the idea here is you have robots that are continually moving around an environment and solving a large variety of tasks. Things like take a picture of someone wearing a red shirt, find me an object to sit in, like a chair, meet someone who has a birthday in January. And the idea is we should be able to deploy this robot across multiple different settings that get transferred both between the tasks as well as between the different environments. We've been applying these methods to robots in the real world as well, in addition to simulation. So here's some videos of our first generation version of Penn service robots. And these are a little bit old at this point. And we have our more recent version of the Penn service robot, which is rolling in right now. And so this is some different renderings of it, kind of the initial concept design through to the actual physical system that we have here, as well as different renderings of outer shells to make this look like much more like a viable commercial product that you might see. And in many cases, we find that the outer form of the robot influences how people treat it as well, where instead of looking at like just a simple, say, research lab output, we can have one that actually looks like a commercial product. And so this is in collaboration with people in the Penn School of Design. There's a large number of people that have worked with us. If you're interested in joining us, we have a bunch of projects which are really interested in finding collaborators on. So this includes 2 projects in open world machine learning, one on visual robot navigation via offline and online RL. This is useful for service robots as well as things like self-driving cars. We're also interested in novelty detection and compensation in these dynamic open worlds. We have problems in collaboration with a couple different departments in the medical school on transfer learning and interpretable modeling for precision medicine. And finally, we're interested in figuring out natural language commands that we can use to actually command these service robots to do real tasks. And if you're interested, please fill out the application there. You can take a picture of it if you wish. Thank you very much. Feel free to send me any questions.
All right, next, Caroline is up next.
All right. Hello, everyone. I'm Dinesh, and I lead the Perception, Action, and Learning Research Group. Much of our research broadly is motivated by this perspective that bringing robots out of really controlled settings like factory automation into the real world, into homes and offices, and so on, is going to be enabled necessarily by advances in visual perception that are closely going to inform how we can build better controllers, and also by the fact that actually acting in the world enables us to see the world better, and therefore it's a kind of virtuous cycle that develops through it. So what I'm going to do today is, well, after introducing the group as it currently stands, these are, between PhD, masters, and undergrad students, we have a fairly sizable group at this point, and I will highlight 3 key results that we've had over the last year. Okay. So here is one. The students that were involved in this are Ed Hu, Kun Huang, and Ole Ripkin. And this is about spatial disentanglement for visuomotor control. And the idea here is to say, if we train a visuomotor controller on one robot for example, a manipulation problem, can we actually then enable that same controller to work out of the box on a new robot that might look very different from it? Right? And this is traditionally a problem that doesn't exist for more standard controllers, for kind of state-based controllers, if you will. But when you do train with a visual state as input, then these appearance differences can actually be a major problem. And so what we want to do is get videos on, or get experience on one of these data sets, on one of these robots. In this case, it's a cheap robot that can actually sit on your desk, this Widow X, and then transfer it to a very different robot, a more high-end robot that looks very different, and see if it can perform the same tasks afterwards. And the idea here is simply to say, it's actually fairly easy for us to disentangle the robot from the stuff that we actually want to affect and move in the world. And so all that we really need to do is treat the process of learning models on one robot as a modular process, where we have one component that is kind of analytical, which we know already well, just based on robot geometry and kinematics. And then the other component, which is the other stuff in the world that we actually want to affect, that's the stuff we need to actually learn models for. And once we've done that, once we've learned a model that's decomposed in that way, that second component, the blue term here, is going to get reused when we transfer to a new robot. And so you can simply plug that new term into the analytical model corresponding to that new robot and actually get it to perform the same tasks that you learned on your first robot. Right? And so this works fairly well. We've tried it against a variety of other baselines that you might think would work, like a domain adaptation baseline. And those methods simply do not enable transfer. Something like this actually works reasonably well for a variety of tasks, including here a simulated pick and place task, and here a real world object pushing task. Okay. The next project that I want to highlight is what we call temporal abstraction for imitation learning. In particular, this paper is called keyframe focused imitation learning. And the student that was involved in this project, aside from collaborators elsewhere, is Aurora Chen. The idea here is to say, very often we do want to have memory in our systems. We want to actually observe a history of observations in order to actually perform tasks in the world. So for example, for this driving task, you would like to track this pedestrian over time, but there are instances in time where that pedestrian is actually not visible to you, right? And so if you only were able to observe one frame, you should not be able to perform these tasks well. And yet we find that in practice, when we build imitation learners with histories of observations as inputs, they actually perform worse. So the numbers that you should be looking at are on this right-hand side beyond the bar, because this is simply the performance on a validation set, but this is the actual driving performance. And it turns out that operating without history works better. And this is a problem that we identified a few years ago now. It's also occurred repeatedly in the literature for about 20 years, and we've been trying to work through a series of solutions over the last few years. One recent insight we've had is very simple. It simply says the imitation error on your training data is better aligned with the eventual performance if you can identify some important frames in your data and mainly focus your imitation error on those important frames, right? And in particular, the way we define those key frames is that they are change points in the action stream. This is actually not an arbitrary choice, but I won't have time to get into it. It's kind of motivated by some connections to causality, shortcut learning, and to out-of-distribution learning. So if you notice that the expert was performing kind of smooth actions for some time, and there was a discontinuity in the expert actions at a certain point, then that's an important frame, and you need to upweight the error at that point. And so we simply upweight the samples corresponding to those change points in the imitation data set. And when we do that, we can actually get significantly improved performance on tasks that have been attempted for some time now, like this visually photorealistic Carla driving environment. And we find that we can particularly address these kinds of problems that arise from adding imitation histories. Okay, the last thing that I want to highlight, if there's enough time, is safety in reinforcement learning. And the idea here is simply to say that, okay, so to set up the context for this, offline reinforcement learning has become a really important topic in recent times. This is promising as one way to think about how we can actually get reinforcement learning to be useful in the world. We don't necessarily have to gather new experience for every new thing we want to solve. We can rely on experience that's already been collected and actually use it to solve tasks. And so that's offline reinforcement learning. What we want to do is build better and safer offline reinforcement learning algorithms. And the idea here is simply to say, let's be distributional and let's be conservative. What that means is that A, we predict the distribution of the Q function, which you would normally do in reinforcement learning is just predicting a scalar. But instead we predict the distribution of the Q function instead of its means. And we also penalize all quantiles of this distribution for states that we identify as unfamiliar. So when we are operating in around the edges of the distribution of states we've already seen, we want to penalize the quantiles of that distribution. And by doing this, you can also instantiate this in a reasonably standard framework, actor-critic algorithms framework for reinforcement learning. You can prove that it converges to a uniform lower bound on the quantiles. And this is known to be a good property for offline reinforcement learning in general. Finally, the thing that makes this safe is that because now we are capturing the entire distribution of returns, you can reason very easily about things like being risk averse or risk seeking. And so we find that sure enough, it actually works. It beats the state of the art for offline reinforcement learning, both in the quote unquote normal setting where we don't care about risks and in the risk sensitive setting where we do care about what happens at the edges of the distribution. So here's a quick demo of how this thing behaves. This is the method that Jason proposed, where we are able to avoid, for example, an obstacle here. This is one of the more toy settings, but it's easier to visualize. But we have similar settings in sort of more complex environments as well. All right, with that, I think I'm out of time, so I'll head on to pass it on to the next speaker. Thank you all.
Next up, we've got Vijay Kumar.
Okay. Hi everyone, my name is Steven. I'm a PhD student in Vijay's lab and also co-founder of a spin-off company from his lab called Truss. And so I'll be giving an overview of the work that we do in the Kumar lab. So our lab consists of a lot of students in CIS, ESC, and MEME, PhD students, postdocs, masters, undergrads, research staff. And we work on a variety of problems, both in theory to applications in the field. And I personally have been able to work on a wide variety of projects, and it's been a great experience for me. And so I'll talk about three themes of the work that Vijay does in the lab. So the first one is autonomy with swap constraints. So SWAP stands for size, weight, and power. This is in collaboration with a lot of other labs in the GRASP lab. But the idea is that we want to make UAVs that are small enough to fit into very cluttered environments, light enough to have good flight time, but powerful enough to run whatever algorithms and sensors that it needs to actually do meaningful tasks in those environments. And a lot of this work is both on individual UAVs, but also in swarm environments. And in the swarm environments, it's a combination of both actual experimentation, both indoors and outdoors of demonstrating formation controls, but also in some very interesting work that other students are doing in these graph convolutional networks for swarms. And so for that, they basically the idea there is to train using machine learning, reinforcement learning on a small network and use that structure to scale up to a larger team. So the second theme is the one that I've personally worked most on, and that's real-time semantic mapping, exploration for autonomous navigation. This is a few different students in the lab, also with other faculty. The idea is to deploy UAVs in very unstructured environments, starting with farms, but now working a lot in forests. The idea here is that the purpose is not just to fly the UAV, it's actually to collect information about the environment. And so it really is a full stack of both the platform sensor choice, the flight algorithms for autonomy, and then finally analytics algorithms to extract out information. And so on the bottom left is an example of the flight stack. And a lot of the recent work has been using the semantic information. So for example, using neural networks to extract out trees to aid that in the localization performance and doing that real time. An exciting thing here is Penn recently received this grant called IoT for Ag, which was exciting because it built off a lot of the work that Vijay and CJ did in the Ag group starting back in 2014, and really brings it to the next level to multiple different robots and interacting with different sensors in the farms. And the third theme is resilience and heterogeneous multi-robot systems. A lot of this is the theory behind it and the simulations to implement them. There are a lot of different problem spaces that are being worked on here. The one that I'll highlight is one called perimeter defense analysis. In this, the idea is to have a team of robots that protect the perimeter. And so the applications are in airspace and defense. And a lot of the work we did there was the precursors to the graph convolutional networks, where we did similar ideas of training smaller teams and then using that to see if it generalized to larger teams. So beyond the research that happens in Vijay's labs, a lot of his students go off and work closely with industry and also form startups. And so I'll highlight two here. So the first one is Exyn, which is a startup that Vijay founded in 2014. And Exyn has built out an impressive UAV and autonomy stack where their main application right now, at least, is in these stope mines. And so they work with a lot of big mining companies in the world globally to use this to actually fly inside these stope mines and map them out to get good volume estimates. And it's done completely autonomously because you don't have line of sight, you can't fly it. And so they focus a lot of their efforts on the actual autonomy stack and shows how a lot of the initial ideas that were developed in the lab have actually made it out into these industries. And then the second startup is TreeSwift. This is the one that I co-founded with a bunch of other alumni from Vijay's lab. This started from my PhD research, which was deploying in these forests. It's work that we started in 2018. And what we do is essentially fly these UAVs in forests to capture information such as timber and carbon. The applications go towards wildfire management and basically a lot of the management of a forest in kind of this climate crisis. And it's been a very exciting journey for me, and I think shows a lot of the interesting work that we do in the lab, and that it's very relevant. A lot of people are very interested in this, and it has been a good experience. One thing I want to highlight is we received an NSF SDR through that, where we collaborate with Penn on that. That's a great tool for academics interested in commercializing research. We're also participating in the Xprize Rainforest, which is a 4-year, $10 million prize to deploy UAV teams in rainforest environments to monitor the biodiversity. And I think TreeSwift is a great example of how I think startups can collaborate with academic labs because even within Penn right now, we have a lot of students who are working on deploying UAVs in forests. But the focus is different, where Truss is very much focused on productizing, scaling, and finding the problems that customers want, whereas the lab is very much focused on the innovations in robotics and how to actually push that frontier. And I think that interplay is a very kind of healthy relationship. Also want to just advertise that I'm giving a talk at Climate Week if you guys are interested in learning more about how I went from basically being a master's student to a PhD and then now starting this company. That's Monday at 2 p.m. And then also just as another plug that we are hiring for interns and full-time positions. That's it for me.
I don't think I have to do. You know, like drag it to the other. What have you guys been doing? Is it projecting in there? Yeah. Oh, it is. Okay. I click go. It's on here. But it's like a little late. Okay. Cool. So I'm going to tell you guys a story about tiny robots, which is what my lab works on. So our story starts here. What you're looking at up here is the leg of a tiny robot. It's a technology that my group built called surface electrochemical actuator, and it's a curling actuator. It curls and uncurls in response to electrical voltages. Now, there's two things that are cool about this tiny actuator. One is that it operates on extremely small voltages. So the voltage scale that this thing uses is about the same as what you would see in semiconductor electronics, like the things that are in your laptop. The other thing that's cool about this actuator is it's extremely small. So if we put a red blood cell up on the screen, it would be about that big by comparison. So it's a remarkably small device. Now we build these little Cs using the same technologies that you would build semiconductor components with. In fact, we build them over in the Singh Center for Nanotechnology. And so just like components for circuits, you can build these little tiny actuators massively in parallel. So this is an array of something like, I don't know, 100,000 million little actuators. They're all wired to a common voltage source. And I'm driving them and they all wave, looking like the legs of what I'll later show you is our future robot army. So because these little guys can be made with the same techniques as microelectronics and they're compatible with the voltages and energy scales used in microelectronics, they make it very easy to take a piece of silicon and turn it into a robot. Basically, all you have to do is add legs. So our group built this simple prototype robot a few years ago. This is now the Guinness World Record holder for the smallest legged robot. It's about 40 microns on the side, which is it's about half a hair's width. It's too small for you to see by eye. And it features a very simple design. There's just two solar cells, very basic piece of silicon electronics, and they've been wired into a set of legs. So it's front legs and back legs. And the concept is that by shining a laser light at each of the two legs, you can trigger the robot to run around the micro world. Let me show you how that works. Okay, so here's one of our robots that's been released. This one's a slightly different design. It's got 4 PVs, but it's the same concept. And if you look at the little solar cell, the little square that's closest to the top of the screen, you'll see that there's this little white dot. So that's a laser spot, and we can control the position of that laser spot with little computer-controlled mirrors. So watch what happens if we cycle that laser back and forth. Off goes our little robot marching around the microverse. Now you might say this thing's not that interesting. I mean, what does it really do? It just walks around. I'll remind you that this is sort of proof of concept work, and what it shows is that you can now integrate all of the technologies that you built, with semiconductor fabrication into small robots. And of course, since we build all these components massively in parallel, we build the electronics in parallel, we build the actuators in parallel. It means that we can build the robots in parallel as well. So here are the final stages of us deploying robots. You can see this is something like 10,000 robots, although you're only looking at about 100 so on the screen. We're using chemicals to dissolve out the surface underneath them, and you can see when it finally dissolves, the robots release into their final structure. Our yield here is something like 90%, so almost every single one of those 10,000 robots we build is a robot that we can later design and we can later control further on downstream. And you can do weird things to those robots as well. So for instance, since these are so tiny, you can treat them like microorganisms. You can come along with a pipette and suck them up, and then inject them back out into other places as you see fit. Now, what does this thing really show? Well, it's proof of concept that shows that any piece of silicon electronics you can build is now something you can turn into a robot. And so what my group is doing now is we're trying to build complicated things, not just little things we shoot lasers at that march around, but things that actually have sensing and computation on board them as well. So we built little sensor packages for these robots. We can make thermometers for them. We can make little voltmeters for them. We can put little LEDs on them so they can blink information back to us. The most sophisticated one of these we're building in collaboration with another group, a circuits group at the University of Michigan, which will actually have a microcontroller and memory on board. It's being built in my lab right now over at Chen. And what's of course cool is when you build anything really tiny and you build it massively in parallel, it starts to get very different than its macroscopic version. All these parts are built massively in parallel all at once. We estimate that each robot actually costs just fractions of a penny. So it's about 0.1 pennies per robot. You can build a swarm with 1,000 robots on it. It'll cost you like 10, $100 or something like that. It's just a radically different system for working because you've miniaturized all of the parts inside of it and you've made it at scale. One of the other things that my lab does, of course, is we're not just building building little tiny robots. It's really fun, but it also has to have some purpose in life. So we're also looking at, of course, technologies and applications for what these robots can do. We've sort of gone into lots of different directions. One of the things we like is like adaptable sensors. There's little cheap nodes. You can send them off and never care if they come back. But they can also go find the best place to make a measurement, or reposition themselves, or explore tiny environments that are hard to get to and relay information back to you very easily. Sort of an example of that is neural interfacing, one place where you really want small stuff, where you really want good measurements and it's dynamic, a changing environment is inside the brain or in the peripheral nervous system. You may not know this, but as you're sitting here breathing, blood vessels are moving the neurons around in your head by quite a bit, by about 70 microns or so. And so it'd really be nice to have sensors that can reposition themselves in order to accommodate that. We have projects of looking at robots as chemicals because they're so small you can't see them. They're effectively like a chemical. You can pour them, mix them, put them together. The most interesting in that space, we have a project about robots that can plate metal onto their bodies so they can attach to one another and form complex structures. And the last thing is regenerative medicine. So using the robots to actually interact with cells kind of one-on-one in a medical space. So we have a project, and most interesting in that bucket is a project folks in the neurosurgery department here at Penn about healing damage in the peripheral nervous system. So the nerves that connect your brain to your, say, fingertip, by pulling the damaged nerves literally where they have to go to rewire them. So using mechanical tension to accommodate that. It's kind of a great example because you might say, well, they're just one cell, why does it matter? Trust me, if you lose a peripheral nerve, one cell matters a lot. You will lose motor function, you will lose sensory function. So it's a very cool application where you can actually have impact. So that's sort of our story. I'll leave this last little movie of one of our little robots running around. One of the things I love about this project is this is just sort of our first generation. We actually have a Gen 2 coming out now, and we're hoping to have a Gen 3 kind of the next year. What I think is really exciting is as we go further and further and further, this little robot is extraordinarily underdeveloped. We did a very bad job engineering almost all of it. We were just kind of trying to show it works. And what's really exciting now is we're coming back and we're doing it right, and these things are getting smarter, better, faster, more and more useful. So I think I probably have a few minutes for questions. Is that, are we, I'm all set. I'm happy to end it here. 30 seconds. Awesome, man. We got a quick question. All right, we're done.
There's a link. Okay. All right, hello everyone. My name is Matt. I'm a PhD student in GRASP here, and I'm really happy to present on behalf of my advisor here on the work that we do in the DARE lab, which focuses on how robots can interact with their environments by touch. So if you think about modern robots that touch their environments and the cool stuff they can do, you might think about Boston Dynamics and their crazy agile feats where Atlas here is running around, jumping, grabbing and touching all these different surfaces in the environment. But what's hidden behind this really cool demo is it took tons of engineers and months to carefully choreograph every single time in every single place that the robot touches the environment. And you can contrast that with our experience as humans, where just all the time we are running and coming into new scenarios and understanding of the world around us and figuring out when, where, and how exactly to touch the environment to accomplish tasks, like these real world human parkour artists are doing to escape some security guard, or like Iron Chef Morimoto here manipulating ingredients to make a dish. And so really in the lab, we're interested in closing this gap between human and robotic performance. And often we find ourselves thinking about the same framework for this, which I'll call model-based control, where really we'd like a robot to come into a new environment like a kitchen. It should be able to quickly model its environment to understand how it can affect it. Then it needs to make a plan to accomplish a task like cooking a dish. And then it actually needs to exert forces at all of its joints to actually take action to execute that plan. And there are tons of challenges at every stage of the pipeline here that we focus on addressing in our lab. And to do that, we combine so many different disciplines. We actually start from the theory of frictional contact. We use that to develop methods of both control and learning, which on the inside are often used techniques related to numerical optimization. And we're really focused in our lab on taking these ideas and putting them on real robotic hardware. So if you're interested in design and implementation of experiments or software for optimization or learning, we'd love to have you join us, and I'll show you some of the things you might be working on if you come to Dare Lab. So what are the challenges that we think about? Well, first, if you want to model your environment, contact makes the world very, very complex. And you don't need a degree in physics or mechanical engineering to understand that. All you have to do is think about a dice roll, where the way that dice hit the ground and tumble and slide is so unpredictable that we essentially treat it as a uniformly random number, which side the dice comes up. And we've investigated some fundamental limitations of common ways of modeling things like this. So even if you want to just like model a simple dice roll, one approach you might take is physics-based simulation. You might be familiar with some of these like Majoko or Drake or Gazebo. And these simulations can get pretty accurate, but their limitations are that they take lots of human engineering to set up, and they always embed some sort of simplification of real world physics that's going to fundamentally limit their ability to be accurate. A totally different approach is to use something like deep learning to model these systems, which theoretically should be able to handle any level of complexity. But we often find that the discontinuities associated with complex often confound these methods and make them very intractable, require lots of data, and very numerically sensitive. And so sort of our flagship modeling technique in the lab is to sort of combine the best of both worlds of these approaches, where we embed deep learning inside of physical simulators and use physical laws to aid the training process. And you can see here that with just a few examples, we can learn realistic motion for dice rolling from real world data. But even if you have a great model, that's not enough to be able to make great plans. We have all these great robots like Cassie here that are beautifully complex to enable them to be very dynamic and efficient. But with all that complexity comes the pain of having to plan how all the 22 degrees of freedom of Cassie need to move in real time. And that can be really computationally intractable. A common approach in legged locomotion is to make a complex robot like this imitate something simple like a point mass, but inherently when you're implementing something simple, you're not leveraging all the complexity of your robot. So Yuming in our lab has developed this approach where you can actually take these simple models and optimize their complexity to be fine-tuned for specific tasks. So here, Yuming's planner is running on Cassie. He's taken this huge 22-dimensional state and compressed it to 3 dimensions, and his fine-tuning to these tasks has resulted in 30% increase in energy efficiency. But even if you have a great plan, that doesn't mean you're going to be able to do great control. So on the left here, we particularly notice that things tend to go awry when you have these really violent collisions between robots and the environment, like in this jumping task. And you can see how Cassie on the left is sort of shaking uncontrollably when it hits the ground. And the reason for this is most of our common ways of stabilizing these plans are extremely sensitive to the times in which impacts occur. And many robots like Cassie don't have contact sensors that help you know when they occur. And so as a result, they overreact to slight differences in these timings, causing them to go unstable. But Will in our lab has actually developed this technique where if you don't have the ability to sense these impacts, you can actually take any controller and get rid of exactly the proportion that is overreacting to the impact and exert all the rest of your control authority to make this jumping action here smooth and stable and reliable. But sometimes that's not enough. Sometimes no matter what, unless you know that impacts are happening, you're not going to be able to react to them well enough to maintain stability. So Alp and Phil in our group have been working on techniques where you can actually integrate tactile sensing into your control formulation and actually respond to impacts as they happen in real time. And here we have this example on a cart pole system where it's able to leverage impacts with the walls on the left and the right to more easily come to rest. Now, all these different projects have been enabled by a really great group of students, and we're a big lab now, even though we're quite a young lab, and we're still looking to expand. So if any of this was interesting to you, you can talk to me after the meeting here. You can go to our website to look for more information about how you can join, or you can email my advisor, Michael, directly. Thanks, and I'll take any questions if there's time. Yes. Yes. It is bad, and a lot of times, you know, our controllers for tracking plans really rely on always being very close to the plan. So what happens is this first impact is at the wrong time, the controller overreacts, and it gets so far off the plan that it becomes problematic for the rest of the trajectory. It does shake a little bit, and that's actually where these inaccuracies can come from. That motion is actually stable, but it's not actually in the, like, I don't know, 200 milliseconds, something like that, of the jump, able to fully damp out those errors, and that's why you can have these mistimed impacts.
Let's give a hand for all of our speakers. We've got 1 minute left. I just want to again thank everybody. Next week we've got part 2 of this research overview. We've got again 9 speakers. Again, it'll be roughly 10 minutes each. Ani Shea, Michelle Johnson, Dan Kochek, George Pappas, Raul Mangaram, Nick Matney, Robert Stewart Smith, Cindy Sung, and James B. Cole. 3 of those are actually affiliates. So it's kind of interesting. This is the first time we're going to have affiliate speakers as well presenting their research. So again, thanks. We've got the food outside, I believe. Yeah, we got food outside. Go ahead and grab some sandwiches and we'll be going.